So, all right, I'm going to try this because I don't want to be insulting. So our next speaker is Simon. And his talk is called Graph States and the Necessity of Euler Decomposition.
Okay, thank you. So my name is Simon Perdrix. And I'm going to talk about graph states and the necessity of Euler decomposition. This is a joint work with Ross Duncan from Oxford. Okay, so what is the context and the motivation for this work? So the context is the program, which has been initiated by Bromsky and Bob Hooker, which is about the categorical axiomatization of quantum mechanics. So in this initial paper, they have proved that Diderot compact clause categories can be used to give an intuitive and formal proof of the teleportation, pointing out a flow of information in this protocol. Then a structure which is called classical basis observable, or even bot structures since yesterday, has been introduced by Bob and Dusko. So here the idea is to use this kind of thing. So all the diagrams that I'm going to present have to be read from the top to the bottom. So here we have a transformation which has one input and two outputs, and the idea is to copy an information. Okay, we have one information and we want to copy this information. So and here we want to delete this information. One input, no outputs. So it's widely used in classical computation, this kind of things. Because of the no-cloning theorem, it's not easy to do the same in quantum computing. However, what we can do is the following thing. For instance, if we define this linear map, so, which includes 1 qubit and produces 2 qubits, and which is defined for those. Okay, so it's a kind of code because if the input is 0 or 1, or obtain 2 zeros or 2 ones. This operation is a valid quantum operation since this is an isometric. And however, this is not cloning. You cannot duplicate information because it applies on the superposition of this one. By linearity, this is thing which is an unstable state. Okay, so we will use this kind of notations in order to represent this kind of operations, which are called copy, and which are basis dependent. As you can see here, this is the copy in the standard basis. Here, this is the copy in the standard basis, but we can choose another basis and apply the copy and define the copy in another basis. In fact, there is a one-to-one correspondence between the basis, the orthogonal basis, and this kind of structures. And it has been proved by Jamie. Okay, so this is an interesting structure that we use. And the last result that I want to talk about in this introduction is the idea which has been explored by Bob Hooker and Ross Duncan, which is to use not just one basis but several bases, two bases, especially in the case where these two bases are complementary or unbiased, we say. Okay, so for instance, if you take the diagonal basis, the standard basis and the diagonal basis, when these two bases are interacting within this kind of equations, this algebra-like equation, and in fact they are defined a powerful graphical language based on these two colors and these bases. And we will use today this language, this powerful language, in order to study the formalism, which is called the graph state formalism. So the idea is to represent a quantum state using a graph, where every vertex is representing a qubit, and where the edges are intuitively representing the entanglement. I will give you a formal definition of the graph states in a few slides. So here with this formalism, we have a graphical representation of entanglement. We are representing an untitled state using a graph. But this is a very powerful and useful formalism. There are several applications. One-way quantum computations. We have heard about one-way quantum computation just the talk before. There are other applications like the protocol, the quantum secret sharing, which has been introduced by Damian Markham and various others. Okay, so the objective during this talk is to give abstract proofs of the fundamental properties of graph states. Abstract means that the proofs are given in the categorical setting, in the graphical language that I've talked about. And why are we interested in these abstract proofs? The idea is that, in fact, there are two objectives. First is to try to reveal some structures, fundamental structures of entanglement, okay, by studying this representation of entanglement. And the other objective is also to refine this language to continue the program of the categorical axiomatization of quantum mechanics. Okay, so that's the end of this introduction. So now I will present you this graphical language, diagrammatic language, and then we will study the graph states in this formalism. Okay, so we are working with diagram. So what is a diagram? It's a graph with inputs and outputs, an open graph. So here we have an example. So inputs here on the top, outputs at the bottom. And all the vertices of this graph are from this set of vertices. So here, so it's just a syntax at the moment. The possible interpretation for these operations are here, this is a copy, okay? Here, this is a state initialization. Okay, we have nothing, we are producing one qubit. Here, this is the dagger of the copy. Here, the dagger of the initialization. Here, some rotation for an angle alpha. And finally, h, it could be Hadamard. Okay, so we have these diagrams. We define some operations on this diagram, compose diagrams. So sequential composition just consists in plugging inputs and outputs and inputs. The tensor is just we just put the two diagrams side by side. And the dagger, which consists in fact in mirroring, putting the diagram upside down and changing the angles as well to minus whenever we have an angle alpha. So it turns out that these diagrams with these operations are forming dagger compact Gauss category with basis structures. So, and it turns out that there are several equations, coherence conditions, that I don't want to go to the details of these equations because the important point is that we have this theorem, which is the spider, which says that whenever we have a diagram like this one without H, okay, H-free diagram, then what is important is just to, this diagram is equal to this one, where we have a big rotation. The angle is the sum of the angles we have here, modulo 2 pi. And what is important is the number of inputs and outputs, and we are just putting enough copies and multiplications in order to have the right number of inputs and outputs. And these two diagrams are equal. Okay, so we don't really care about the structure inside the diagram because it's equal to this one, which would be represented just like this. A big rotation with an arbitrary number of inputs and outputs. So this spider theorem has been proved by Eric Paquet. And Bob. But Bob is everywhere, so you can add Bob.
Do you mean Bob Kuka?
Yes.
Oh, okay.
Actually, there is some abstract version of it by a guy called Steve Leck.
Okay.
So you have to then know a lot of category theory too.
Okay, so two special cases. So if the angle is 0, we just put a small dot. And if the angle is 0 and there is just one input and one output, this is the identity. Okay, so we have this theorem, this spider transformation. And but it works just for diagrams without H. So now what happens when there is an H? So the properties of H are the following. First of all, H is self-inverse. H squared is the identity. And in fact, we will use this H in order to define a new basis. Like we will define the red basis by taking the green operations and conjugate them by H. So for instance, here this is the red state initialization, which consists in applying the green state initialization followed by H. Here this is the red copy, so we are applying green copy with H before and after the copy, and so on. So we are defining the red bases, the red operations like that. And it turns out that the language we obtain is very symmetric for the two colors, because there is also a red version of the spider theorem. And now what happens when green and red are interacting? So we have the following properties. So first of all, we have that green copies red. So it means that if we have this red state initialization followed by a green copy is equivalent to two green initializations. We have this bialgebra equation. I have no interpretation for this, but this is very powerful, so very interesting. And we have also this pi commutation, which says that if I apply a pi green rotation followed by a red copy, then I can first apply the red copy and then the pi green rotations. Notice that this property is true just for pi, not for an arbitrary angle. If you change the colors, you obtain the same properties are also true, okay? Since the language is symmetric for the two colors. So, okay, and there are different ways to define all these properties. Here it's one way to define the interactions between the two colors. Okay, so now what about quantum mechanics? It turns out that we can interpret all these diagrams in the category of finite dimensional Hilbert spaces, where here the state initialization is an initialization in this superposition. Here, this is the copy in the standard basis. This is exactly the map that I have defined here. The green rotation is a Z rotation, and H is polymorph. And using this, we can see that the red rotation is an X rotation. Okay. And if we compose H in this green rotation, we obtain this map, which is nothing but control Z. Okay, so it means that here we have a universal set of unitary transformations, the rotation, H, and control Z. So it means that any unitary transformation can be described in this language.
Sorry, what is the horizontal lines connecting to the H?
Okay, so it turns out that we can prove that if you do something like this, we can prove that this is equal to this. So since we have this equation, we are just writing this. Okay, so now we are ready to talk about graph states in this formalism. So what is a graph state? So we have a graph G, and we are defining a quantum state Kg as follows. So for instance, we are considering this triangle. So for each vertex of the graph, we are creating a qubit in this state, in this superposition state. And then for every edge of the graph, we are applying a control Z on the corresponding qubits. Okay, so here we are creating 3 qubits in this state, and then we are applying control Z here, here, and here, the corresponding qubits. So this is the definition of the graph state. In the graphical language, since we have seen that the initialization of the qubit is exactly this operation, and the control Z can be represented as follows, we obtain that the definition of the graph state of the triangle is this one, in a circuit-like representation. And using the spider, we can rewrite it as follows. So just a triangle with edges. Okay, so in fact we don't really care about the formal definition because there is a graphical definition. It just consists in associating with every vertex of the graph a green dot, and for every edge we put an H between the corresponding vertices, the corresponding dots. Okay. And we obtain the graph state in the graphical language. Okay, so now we have the definition. What about the properties of this graph state formalism? The first interesting property is the fixed point property, which says that if we have graph state and if we're applying x rotation, a pi x rotation on the vertex and a pi z rotation on its neighborhood, then the state is unchanged. So for instance, for the triangle, here this is the representation of the triangle in the graphical language. Okay, just one point here. If we look at the previous representation of the triangle, all the wires, there is no input and 3 outputs because this is a graph, this is a quantum state preparation. Okay, but however we are working with a compact closed category, so we can turn some output into inputs. We don't really care about that. So that is why we represent the graph state using 1 input and 2 outputs, but it's equivalent. Okay, so we have here the triangle, the representation of the triangle, and this property says that if we are applying this pi red rotation here and pi green rotation on the neighborhood that is on these two dots, then the state is unchanged. Okay, so this is how the property can be represented for the triangle in this graphical language. So how can we prove this property in the graphical language? So the proof is as follows. So we use this pi commutation property, that is, we can push this pi through these green dots. We obtain 2 copies of the pi. Then H is changing the basis, so we can push the pi rotation through the H and we obtain the green pi rotation. Do the same here and here. Now we can use the spider in order to group all these green things and these things as follows. And since the angle is defined modulo 2 pi, we obtain exactly this one, okay, which is the original triangle. So it's the proof for the triangle. It turns out that the proof for any graph can be obtained by induction. Okay, so it's the first property. But the more interesting property is the Van den Neff theorem, which says that if instead of applying pi rotation, we are just applying pi over 2 rotations on the graph state. So we are taking one vertex u, we are applying x rotation, so pi over 2 x rotation on u, and the minus pi over 2 rotation, z rotation on the neighborhood of u, on all the neighbors. And then we are changing the state, but the state we obtain is described by this new graph, which is the local complementation of G. So the local complementation of a graph G according to U is defined as follows. So this is the symmetric difference between the graph and the complete graph on the neighborhood. This is a transformation which has been introduced by Boucher, but there is, maybe I can explain it as an example. So, let's say that we have this graph. So the local complementation on U is a local operation, so it will act only on the neighborhood of U. And this is a complementation, so we are complementing this neighborhood. It means that since here there is an edge, we are removing this edge. Since between these 2 vertices there is no edge, we are adding 1 edge. Here there is no edge, we are adding 1 edge. And the rest of the graph is unchanged. So the local complementation is this transformation. So for instance, if we are starting from the path and we are applying the local complementation here, we are adding this edge. Okay, so it's an important property because here we are just applying local operations. So it means that these two graphs are LU equivalent, so it means that they have the same entanglement. Okay? The entanglement is invariant by local complementation. This is the meaning of this theorem. Okay, so this theorem can be stated into the graphical language as follows. So here is the triangle. Here we have the path on which we are applying this pi over 2 red rotation and minus pi over 2 green rotations. So we can represent this theorem, and we have tried a lot with Ross to prove this theorem in the graphical language, but we failed. Since we are not able to prove it, we have decided to consider a new equation, and if it is helpful. And this new equation is the Euler decomposition of H. So, you know that any unitary transformation can be decomposed into Z, X, and Z rotation. So for Perdrix gate, it's this decomposition using minus pi over 2 rotations. So this equation is true in the finite dimensional Hilbert spaces. And in fact, we will use this equation, these new equations. What are the properties of this Euler decomposition? So first of all, since the language is completely symmetric in terms of we can exchange red and green, it's not surprising to see that if we have this equation, we also have this one. So the proof is here. We are starting from H. We are adding this thing, minus pi over 2, so it's the identity. We are pushing this rotation through the H. We are changing the color. And then we are using the definition of H here, this equation. We are simplifying and we obtain exactly what we want. Okay? So it means that this Euler decomposition is not unique. We have two of them here. Another property of this Euler decomposition is the following one. It allows to represent a pi over 2 rotation, a red pi over 2 rotation, using a green minus pi over 2 rotation. It makes connections between the two colors as follows. So the proof is here. So we are starting from this side. So that so we can change the color this by minus pi over 2 rotation using an H. Here we are replacing H by one of the two decomposition we know, so the one with red, green and red. Then here these two rotations sum to pi, and so we are using the spider in order to expand this part. Thanks to the pi commutation, we can push this pi through the green dot, obtain this. And now we use the fact that the green copies red. So we obtain one branch here, one dot here, and we obtain this new diagram. Okay. So here it appears something new, which is a disconnected diagram with no input, no output. In fact, this is representing a scalar. So it has to be treated carefully, but I don't want to go to the details of these kind of things today, so we'll just ignore it. And so up to this is the proof of the property. Okay, so now we are ready to prove the Van der Neef theorem, at least for the triangle. So, and in fact, we have proved that if we have this Euler decomposition of H, then we can prove the Van der Neef theorem. So we are starting from the triangle. We are replacing H by its decomposition. Using the spider, we can push this pi over 2 rotation through this green dot here, and the same here. Now we also push the H's here through the green dot between the red dot. Now, since we have this square, we can find bilateral equation. So we are here. So the application of bilateral equation. So we are pushing this h back to the bottom. And now we can use the lemma that we have proved before about the connections between the pi over 2 red rotation and green rotations, and explain exactly what we want. That is the Van der Neef theorem for the triangle. So here it's the proof for this special case, and by induction we can prove this property for any graph. Okay, so I've put this one. So it means that if we have this Euler decomposition, then we are able to prove the Van der Neef theorem. So the Euler decomposition is sufficient for this theorem. But in fact, we have also proved that this is necessary. That is, if we are able to prove the Van der Neef theorem, which is this equation, then we are able to prove this H decomposition. So I will not go to the details. So we have proved this equivalence between the Euler decomposition and the Van der Neef theorem. And there is one missing part, which is that do we really need to use this Euler decomposition? That is it possible to prove this Euler decomposition in the graphical language? Okay? Or is it something new? Is it a new rule, or is it possible to derive this equation from the graphical language, the axioms of the graphical language? And the answer is that this is a new rule. In fact, we have considered another interpretation of the language, of the graphical language, where the interpretation is almost the same, except for the rotations. Now we are interpreting an alpha rotation as a rotation of angle 2 alpha. Okay, we are adding this 2 here. It turns out that all the previous, it's a valid interpretation of the graphical language. Okay. However, this H decomposition is not verified for this interpretation. So it means that this Euler decomposition cannot be proved in the graphical language, because there is an interpretation which is valid for the language in which this interpretation doesn't hold. Okay, so to conclude, I presented an abstract proof of the Van der Neef theorem, pointing out that this Van der Neef theorem is connected to the H decomposition, the Euler decomposition. In fact, the Euler decomposition is a sufficient and necessary condition for this theorem. And moreover, we have also we obtained a refinement of the language by adding this new rule. So, what about the perspective? Turns out, so this Van der Neef theorem says that the entanglement is invariant by local complementation. However, it's not a characterization of the entanglement, because there exist graphs which are not locally equivalent. That is, we cannot go from one graph to the other using local complementation, but which are representing the same entanglement. Okay? So the local complementation is not characterization of entanglement. So the objective here is to try to refine the language in order to capture these new cases, okay, this kind of graphs. And moreover, one of the main limitations of the graph state formalism is the expressivity of the language. It can represent only few states using a graph state. So since here we are in a language, in a graphical language which is universal, which we can represent any quantum state in this graphical language, so we can try to look at properties of a more general class of states. And just to finish, I want to, if you want to play with these diagrams, you can have a look to this page and play with Quantumatic, which has been developed by Lucas, Ross, and Alex. Thank you for your attention.
Any questions? Yes.
How do you get the coupling equation and the biaxial equation? Do you get it by matrix calculus?
Yes. Yes.
Okay. So is your graph quite different from a quantum circuit? A quantum circuit is also a graph and is also calculated by matrix.
Yes. So you can encode the circuits in this formalism. It's easy. So, for instance, if you are considering circuits which are with a set of gates which are exactly these gates, that is the Z rotation, H, and control Z, then you can translate any circuit directly into the graphical language. The main difference between a circuit and this formalism is that the circuit has to be acyclic, whereas this is not the case here, basically.
So I understood that the graphs do not allow multiple edges.
These graphs?
Yes?
No, there are simple graphs, non-oriented graphs.
But
Only the qubits, right? If you go to higher dimension, then you can have weights on the edges.
because the building blocks allow you to construct double edges.
Yes, but they will cancel out.
Okay.
There are two edges, so it's just the same as no edges.
Okay.
Are there any other questions? Yeah. All right, let's thank you